Welcome back to Chem 4300. In this video, we're going to continue Chapter 8 on classical wave motion. We're going to be talking about the physics of standing waves. Now, if you're a musician, you're probably already familiar with a number of properties of standing waves. For example, say you play the violin. You know that as you bow the string, you set it into motion, you create a wave pattern, but you also know that at the bridge, the amplitude of that wave is forced to go to zero. And similarly, when you press your finger down on the string, you're also forcing the amplitude to go to zero. So what you're doing is you have two boundary conditions, one set by the bridge, but one set by your finger, which you can adjust. And that set of boundary conditions limits what kind of vibrations the string can have. Now, pretty much, when we look at any musical instrument, there's some set of boundary conditions that are in play that allow that instrument to have the properties that it has. So whether you're talking about a violin string or a drum head or a wind instrument like a flute or an organ pipe, there's some kind of boundary conditions that are going to create these standing wave patterns. Now, inside a standing wave, what you find is that there is harmonic motion all along the wave, and every one of the points along the wave, that harmonic motion has exactly the same frequency and the same phase. So if you looked at as a function of position, the time dependence would be identical all across the wave. Now the amplitude will be varying, but the time dependence will be the same. Now one way you can think about standing waves is as two traveling waves coming from opposite directions, coming together with equal amplitudes to create a standing wave pattern. We'll talk more about that later in this chapter. Now for now, what we're going to do is we're going to dive in and solve the differential equation and use these boundary conditions. So we'll start out by coming up with a guess, a trial wave function that we can plug in and see if this is a good solution for our wave function. And the one I'm going to use is this one approach called separation of variables. This is very common for the wave equation to use this approach. And as you know, with differential equations, there are certain guesses that you make, and then you sort of fill in the rest. And if they're good guesses, then they'll work, and you just have to make a few adjustments. But if they're bad guesses, they won't work at all. But this guess here of doing separation of variables tends to work often when you're looking at the wave equation. So we're going to take this and run with it. So we're going to take this function here, where we have a position-dependent only part. This is called the stationary state wave function, and a time-dependent part. And we take the product of those two functions and we form the full wave function. Now, if you take this function and you plug it into the wave equation, you can see what's going to happen. And it's actually pretty obvious. You can see that when we take the derivative with respect to time, well, the position-only dependent part will just slide right through, and we're just going to be left with the second derivative with respect to time right there. And similarly, on the other side, when you take the derivative with respect to position, the time-dependent part is just going to pass right through, and you're just going to have the second derivative with respect to position. So this is the result. You could probably do that in your head by just making that substitution. Now what I'm going to do next is I'm going to move the time-dependent part over here and the position function over here so that I can write it in this form, where now I have everything that depends on time on the left and everything that depends on position on the right. And there's no mixing of the two variables. All the time variables are over here, all the position variables over there. And that's really important, because what we have now is that a condition where whatever is happening with this function, with its second derivative and then divided by the function, whatever happens here has to be exactly equal to what's happening on the right side with position. And the way that that can be true is to have this whole thing equal to some constant. So this guy is equal to this guy is equal to a constant. So this is called a separation constant. So in this particular case, I'm going to set the separation constant equal to minus omega squared. Now that might seem a little bizarre, and if you wanted to, you could just set it equal to some constant c, but I know what's going to be happening next, and we're going to want to go back and readjust it to this value that looks like minus omega squared. So I'm just going to put it in there now, and just trust me, you could use c, but you'll want to set it back to minus omega squared later. So let's continue now. There is just simply a constant here that we're going to use. Excuse me. So what I get then is I take this partial differential equation, these two partial differential equations equal to a constant, and I can rewrite them as these two equations. Now what I've done, because I was able to pull all of the time dependence on over here and all the position dependence over here, is that I turned a partial differential equation into two ordinary differential equations. So now these partial d's become just regular d's, the ordinary d's there. And so we get this differential equation for the time-dependent part and this differential equation for the position-dependent part. So now we have two separate problems we have to solve with our boundary conditions. So let's focus on the time-dependent part. Here's the equation. We just need to solve that differential equation to get the t function. So we're going to propose a solution, and I'm going to propose a solution that's just some oscillation, A cosine ct, where c is some undetermined constant, B another undetermined constant times sine ct. We take this solution, proposed solution, and we plug it into our differential equation, and we get this result. So we see that for this result to be equal to 0, we can achieve that easily by just setting c squared is equal to omega squared. And now you start to see why I picked that constant as omega squared, because that means that the constant c is equal to omega gives us this solution here. All right, and that is a lot nicer than if I started earlier with just some separation constant of c. By setting it equal to minus omega, I get this nicer result here. So now we have this result, and what we're going to do is a little bit of algebra. So I'm just going to rearrange this, just some trig identity here, and algebra here, and I'm going to take this guy and turn it into this guy here. So you can just verify that for yourself here. But I'm going to write the function in this form here, where now I have a phase and omega t in the argument for the cosine with some constant c. Okay, so we still have an undetermined constant here too, which we'll come back to. Now let's move over to the position-dependent part. There's our differential equation. Once again, we'll propose a solution. So I have some unknown variables, d, f, and k, and I'll plug that into the expression up here. And if you do that, you end up with this equation. And you see, just like before, in order to make this equation true, go to 0, we're going to set k squared is equal to omega squared over vp squared. So this condition here is what we get for satisfying this solution. So getting solutions that satisfy this differential equation. And so now we have this result for x. So now we have a solution for t that satisfies its differential equation. We have a solution for x which satisfies its differential equation. So now we move on to the boundary conditions. So along x, we know that the amplitude has to be equal to 0 at x equals 0 and 0 at x equals L. So if we look at the x function, if we take this as our function, we can substitute in x equals 0. Well, cosine of x equals 0 is 1. Sine of 0 is 0. So that leaves us with this equation that x is equal to d. And we know that the amplitude has to be equal to 0. So it must be equal to 0. So that tells us that d has to be equal to 0. So that gets rid of this term completely. And next we move on to the next boundary condition, which says that x equals to L, that we have to be equal to f sine kl, because we substituted in L for x here. And that has to go to 0 because that's the point where we know the amplitude is 0. And here we see a little bit more trickier problem. This one was obvious, but here we see that the only way we can make this argument go to 0 is if k times L is equal to some integer multiple of pi. So we write that condition here. K times L is some integer times pi, where n could be 1, 2, 3, and so on. So what we're finding is that there's a series of solutions that satisfy this condition. So there's not just one solution, but there's a series all labeled by a different value of n. So what we're going to do is we're going to write down our series, which now is dependent on which n that you're using, and that's going to be x sub n is equal to some amplitude. We'll just give f a subscript 2 for that particular mode. And so this n here, and then an n on the k, where k is now subscripted n to indicate it's n pi over L. All right, now we've come up with this result. So we have a set of solutions that satisfy the boundary conditions for x equals 0 and x equals L. We can also use our relationship that we learned in the first part of the chapter, that omega is equal to Vp times k. So we can take our substitution here of k here, and we can get that omega is n pi Vp over L, or if you want to use the Greek nu, the frequency, instead of the angular frequency, it's n Vp over 2L. Okay. So now we're going to take the spatial dependent part, the x dependent part, with our time-dependent solution that we found earlier. And now, since we know that, I'll go back to the previous slide, that our omegas are also going to be indexed by the n solution. So we saw that because k depends upon n, then because omega depends on k, then omega now depends upon n. So everybody now has an n dependence. And so now we have the x solution, the t solution, all dependent upon n, and we form our solution, which is f of n as a function of x in time, position in time, is the product of these two guys, and we'll write it in this form, where I'm just going to sort of multiply these two guys together and just make a new amplitude a sub n, and that's our solution. So that's one of the solutions, I should say, that's, you know, for different, all the different possible n's form a series of solutions for the standing waves. It's a complete set of solutions depending on n equals 1, 2, 3, and so on. In fact, I'm going to put this up right over here. So here's the solution that you get for n equals 1. And this is a wave that starts at 0 and ends at 0, as they all do, as we expect them. But now it has an amplitude that goes to a maximum in the middle. And I'm drawing sort of the excursion of it. Here's the plot. So if I'm just plotting the function at an instant in time, it will go from this value up to here and all values in between, but it will oscillate between these two extremes. So the n equals 2 will look like this, and so there's a node in between. N equals 3 will have 2 nodes, n equals 4 will have 3 nodes, and so on. So that you might recognize this. This is something we solve in the freshman chemistry class when we're talking about particle in a box, but it's the same solution for a standing wave pattern for any arbitrary kind of wave, not just in quantum mechanics. So this is the solutions that we get, and we have all of these solutions are valid solutions, and it goes out to effectively infinity for n. So now what we're going to do is we're going to look at how you might take a string and decompose it, go back here, into the possible some linear combination of these solutions. Now, when you play a string, so this is an example on a harp, when you play the string, you're not just setting up one of these modes. In other words, when you play the string, it's not like you pluck the string in such a way to create only that oscillation. You're creating some linear combination of these oscillations, and that's what actually makes the sound very interesting, to be honest, right? If you just had one of these modes on your string, it wouldn't sound anywhere near as nice as it does when you have what you have when you pluck it. So here we have sort of a picture here where somebody's playing a harp and they're about to pluck a string. And so what we have, say, at the moment right before the string is let go, is that you have the string being pulled out to some point, say where the finger is pulling the string, and then down to the other side. So it's fixed at the top and the bottom to go to 0 amplitude here, but the string has been pulled out. So this is a wave function. This is the wave function at time 0. And at time 0, that wave function can be decomposed into some linear combination of these guys. So this is a valid wave function for our wave equation, and it can be expressed as some linear combination of all of those harmonic solutions that we just determined here. These what we call the normal modes. So how are we going to do that? How are we going to decompose this guy? Well, to do that, we need to apply something called a Fourier series analysis. So we know that whatever function we have, whatever shape the string takes on, it has to be expressed as some linear combination of all of those harmonic solutions. So A is the amplitude of each normal mode contribution. So what we do is what Joseph Fourier taught us how to do, is that for this particular example here, a Fourier analysis says that if you take the integral of your function, so what we want to do is we want to figure out from the function what these amplitudes are. So if you take the function, so in our case here, a function is this, and we plug that function into this expression, and we do this integral for all the different n values, then you'll get the amplitude of each harmonic contribution to that shape here. So let's look at how that works. So we're going to take that shape, and we're going to calculate the first three normal mode amplitudes that contribute to making that shape. So if I start out, first I have to write that wave function that describes this. If you look at this, it's not so bad. What you have is a straight line up to L equal L over 2, right? So that means that it has a straight line with the slope of D over L over 2, where D is the initial amplitude that we pull the string out to. And that's valid over this region. And then on this side, we just have the string going down with the opposite slope, but now it intercepts up here with an intercept of 2D. So this is the function that handles it from this side on, and that's our function split into two parts. So we're going to take this description with these two parts and plug it into that Fourier analysis. So there's left of the pluck, right of the pluck. And if I plug them in, then I'm going to take my integral, take this guy, plug it into here. My integral is going to break up into two parts. There's the left part, and then there's the right part. So this is integrated from 0 to L over 2. This is integrated from L over 2 to L. So I'm going to leave it for you to do this, but if you evaluate this integral, you can evaluate for generic n, for arbitrary n, you can evaluate that an is equal to 8d over n squared pi d squared, and pi squared sine n pi over 2. That's the amplitude for n equals, you can calculate n equals 1, n equals 2, and so on. So if I plot that, actually, let me see if I plot that function, the Fourier series analysis, this guy right here, this is what it looks like as a function of n. So this is the amplitude. It says that if you initially pluck the string like this, then you will create a significant amount of the n equals 1 mode. You have none of the 2, but then you create a negative amplitude of the 3 mode, and then you get none of the 4, but you get a little bit of 5, and so on. So you can check this out numerically here, but you can see how these guys come out. So this is what's called a Fourier series analysis of this particular initial shape. Now, after you let go of the string, then it's going to change, and you'll have each of those, the string shape will change, and as it vibrates with time, but the contributions from each of these guys will remain the same. There'll be this amount of 1, this amount of 3, this amount of 5, and so on. And that mix of all of those harmonics, all of those modes, is what gives the string with that pluck its particular characteristics that might make it pleasing to hear, as opposed to just one harmonic on the string. Okay, so I think that is it. In the next video, I'll look at some demos, apps that we can show some of this behavior.